Hello, my name is Mohammadreza Mohseni. Today I'm presenting our work named Can Self-Training Identify Suspicious Ugly Duckling Lesions by Jordan Yap, William Yolland, Arash Koochek, Stella Atkins, and myself. Let's first define what do we mean by ugly duckling lesion. A lesion is called ugly duckling if it looks different from other skin lesions in its proximity. The difference can be either in size, shape, or color. Figure A, B, and C illustrate example of such differences. Previous research has shown that ugly duckling sign has a correlation with the existence of malignant melanoma. Automated identification of ugly duckling lesions allow dermatologists to make faster and more accurate decisions. It is important to mention that such tool can be useful for both teledermatology and clinical visits. Ugly duckling detection problem can be modeled as an outlier detection problem. As we mentioned earlier, ugly duckling is defined as a lesion which looks different from other lesions in its proximity. In order to identify ugly duckling lesions, we trained a variational autoencoder, also known as VAE, on skin lesion images. Here, the VAE is given an image as input and is tasked to reconstruct the same image as accurate as possible in the output. Given that size of VAE's latent space is much smaller than the number of pixels in the image, VAE has to choose a subset of features which describe the majority of the data as good as possible. This property leads to accurate reconstruction of common skin lesions and poor reconstruction of ugly duckling lesions. Finally, by observing the reconstruction loss, we could identify ugly duckling lesions. In this slide, we can view an initial version of ugly duckling detection pipeline. First, the input TBP image is given to a detection module. This module is a single-shot multi-box detector. It uses ResNet 18 as backbone and feature pyramid network for improved multi-scale detection performance. The detection module detects every skin lesion visible in the TBP image and passes their location to extraction module. The extraction module then center crops each skin lesion into 64 by 64 patches and passes these images to the outlier detection module. Finally, outlier detection module identifies ugly duckling lesions with the help of a variational autoencoder as described in the previous slide. As we mentioned earlier, our approach relies on three major steps. First, extracting all of the lesions from a TBP image. Second, self-training a VAE on all lesions of a single patient. And finally, selecting the lesions with high reconstruction loss as ugly duckling. However, when we tested our initial algorithm, it suffered from two major issues. First, lighting conditions and lesions locations heavily noise the results. For example, lesions which were located on the edges of the body or in the shadow were identified as ugly duckling. Well, this wasn't unexpected, since the majority of the lesions are not on the edge of the body or not on the shadows. Also, it took the pipeline a long time to answer each query. We needed to self-train the VAE from many epochs in each query and this took around 2 minutes. In order to fix the issues mentioned in the previous slide, a segmentation module was added to our pipeline. This module segments the skin lesions extracted from the TBP images, image. Adding the segmentation module greatly reduced the noise in our results. We also found that by pre-training the VAE on 300 unlabeled TBP images, we can greatly reduce the self-training time. A pre-trained model already has information on how to describe the lesions in general. It just needs to learn some patient-specific features, which take much less time to learn. Finally, we observed that by calculating the average of the feature vectors for all lesions in a TBP image and calculating the distance of each lesion from the average feature vector, we can better identify ugly duckling lesions. In this slide, you can find the final version of our pipeline, which uses segmentation module. This module uses a smaller variant of UNet to segment all of the lesions before passing them to outlier detection module. In order to evaluate our pipeline, we perform both qualitative and quantitative analysis of our results. In this slide, we can see a TBP image on the left and our algorithm's corresponding prediction on the right. The number above each lesion shows the distance of the lesion's feature vector from the average feature vector of lesions in this TBP image. The lesion shown at the top left has the highest distance from the mean, and the lesion shown at the bottom right has the least distance from the mean. Another example is also shown here to illustrate our algorithm's prediction. As you can see, noises such as lighting conditions and lesion's location do not play a huge role in the ranking anymore. We quantitatively evaluate our work on 75 TBP images. All of the lesions in the TBP images are labeled as either ugly duckling or not ugly duckling by a board-certified dermatologist. We obtained our data from two sources. First, the internal data, and second, the SD dataset images. The pie chart on the left shows how many images came from which source. The bar chart on the right shows the number of TBP images containing specific number of ugly duckling lesions in our evaluation dataset. Evaluation of our work can be done using two sets of metrics. Ranking-based metrics evaluate how effective our proposed ranking is. We use mean average precision and mean reciprocal rank over TBP images to report our ranking's accuracy. In order to be consistent with the previous work, we also report the 3 agreement and 7 agreement between our ranking and the ground truth. 3 agreement for a TBP image is 1 if there exists any ugly duckling lesion ranked between first to third, and otherwise it's 0. 7 agreement is also calculated in the similar manner. On the other hand, binary classification-based metrics look at the ugly duckling detection problem as a binary classification problem. These metrics include accuracy, sensitivity, and specificity. Since ranking-based evaluation is not meaningful, if no ugly duckling lesion exists in the TBP image. We only perform ranking evaluation on the TBP images with at least one lesion labeled as ugly duckling. We measure each metric for each TBP image and report the mean of the metric over all TBP images. As we mentioned earlier, another approach to evaluate our work is to use binary classification metrics. In order to obtain binary predictions from ranking, we apply the threshold to calculate the distances. Any lesion with the distance above the threshold was predicted as ugly duckling. Our threshold is calculated based on the mean and standard deviation of distances. When calculating the threshold, we added the mean of distances with the minimum value of mean and standard deviation of distances. The intuition behind taking the minimum of 2 is to encourage the model to predict more ugly ducklings in cases with high standard deviation. We observed that high standard deviation of distances correlates with high number of ugly duckling lesions. We measured accuracy, sensitivity, and specificity of the binary classifier in 2 scenarios. In the first scenario, each metric is calculated over all the lesions from all TBP images. In the second scenario, also known as macro averaging, we measured each metric for each TBP image and reported the average over all TBP images. In this work, we showed that, firstly, ugly duckling lesions can be accurately identified from TBP images with the help of self-training. We also evaluated our work against 75 images from 2 data sources. Finally, we presented 2 types of metrics for evaluation of ugly duckling detection algorithms. Future work will involve, first, using the result of our work to enhance the performance of melanoma detection from TBP images. Second, investigating if features extracted by the VAE correlate well with size, shape, and color of the lesions, as mentioned earlier. Third, investigating the effect of replacing these features extracted by VAE with handcrafted features. And finally, publishing a large public dataset for better evaluation of such algorithms. You can find a list of our references here. Thank you for your attention.